Alright, so to finally answer the question of magnets, how do they work? So we're going to do one final video. This is sort of bonus material, nothing that you'll be tested on, but these are really some of the details of magnetism in materials. And as usual, we're going to finish this last video with a blind bag. I've got some Lego minifigures to open today. I'm pretty excited. I love Legos. If you've been in my office, you know this already. So we'll crack that here in just a few minutes. But to our question now, magnets, how do they work? And specifically magnetism in materials. And before we get into the details, let me give you a quick primer on a little bit of quantum physics. Because really, this all comes down to electricity. As we said in the very first video, how do you produce a magnetic field? A changing electric field. And the most common situation of a changing electric field is a moving charge. And what are everything made of? Protons, neutrons, and electrons. Magnetism, it turns out, comes from the electrons in objects. And whenever things have electrons, they stack up in orbitals or shells around the nucleus. I'm not going to get into too many details there, but for today's discussion, what you need to know is those electrons form or line up into those shells in pairs. And when they do so, they can have two different orientations, spin up or spin down. And once one has picked one of those, if another electron's going to pair up with it, it has to go in the opposite orientation. And they form electron pairs, one up, one down. And that sort of combines for a neutral situation. However, what if you have an odd number of electrons? You've got to have one left over. And that's really going to be the key to a lot of this. So let's discuss magnetism in materials with that in mind. So the first type of magnetism I want to talk about is diamagnetism. Now, diamagnetism happens in everything, but it can be overpowered by other types of magnetism in certain types of materials. So diamagnetism only affects pairs of electrons. It doesn't affect single electrons. So it only affects those electron pairs that have bonded together in opposite directions, which have left them with very little what you call a magnetic moment. But don't worry about that. You can think of it just as roughly canceling out. That leaves the material weakly magnetized, and it magnetizes in such a way to oppose the applied field. So examples of these things are gold, quartz, water, copper, and air. And the way it would look is really how it behaves in an external electric field. That is what defines these forms of magnetism. So if you drop something into a magnetic field and it opposes it, that means it's going to feel a force away. So this would be the north end of our applied field. With field lines coming this way, our magnet has field lines pointing outwards. And remember, if those field lines point towards each other, they push away. We've got north field lines trying to go into north. You can't go into north. You can only go into the south end of a magnet. So they push away. The next type is paramagnetism. Now, paramagnetism happens in materials with unpaired electrons. Unpaired electrons align with the applied field, reinforcing it, causing the material to be attracted to the field. So if you remember, we looked at those little loops, and you can imagine the electrons going around the nucleus like a little bit of a loop. It doesn't really go in a perfect circle, but roughly it prefers one direction or another. And if we consider that moving electron as our current loop, we then have a B field in one direction. And that B field aligns with the external magnetic field so that the magnet has its north pointing in the same direction as the previous one. We end up lining up north-south, and so on. And if that south pole is pointing towards those north field lines, it gets pulled inwards. So paramagnetism is what happens if you hold a magnet next to an object and it is attracted. However, you take it away and it's no longer magnetic. You take the magnet away, the object falls down, it's right back to where it started. It only has this property while the magnetic field is there. Lastly, we'll talk about ferromagnetism. Now, ferromagnetism is that which you are probably most familiar with. That ferro, that prefix comes from ferrous, which actually refers to iron. Remember I mentioned when we were talking about lodestones how iron is a special material? Well, things that are like iron, or things that have ferromagnetism, are also things or materials with unpaired electrons. Only in ferromagnetic objects, those unpaired electrons remain aligned even when they're removed from that external field. So they can become permanently magnetized, permanent being a rough word there. They eventually fall out of magnetism, but they will become magnetized for a longer amount of time. You can usually remove it by heating them up. You can help keep it magnetic by keeping it cold. But you put a ferromagnetic material in a magnetic field, all its extra electrons line up. They have all of their electrons spinning in the same ways, their magnetic fields pointing in the same direction, and they'll then remain that way. So you can produce a new magnet by putting a ferromagnetic object into a magnetic field. And so those are the three basic types of magnetism that objects can exhibit, and they're all determined by placing that material into a magnetic field and observing how it behaves. If it is weakly opposed, it's diamagnetic. If it is more strongly attracted to that external field, it's paramagnetic. And if you take that field away and it remains magnetized, then it is ferromagnetic. This thing would have fields of its own after the magnetic field has been taken away from it. So that concludes our chapter on magnetism. Let's end today's lecture with some fun, a Lego minifigure. I'm excited. There's so many fun variations on these. Oh, this looks like one my son will enjoy. Looks like we got a firefighter, a lady firefighter. And she has a megaphone to talk to people. So he is currently passed out on the floor, taking a nap, but I'm sure he'll be excited to play with that when he wakes up. As usual, don't hesitate to email me with any questions or concerns, and I'm always available to do some video tutoring if you guys want to register for a slot on my website, or not my website, on the Calendly website, calendly.com/Ryan-Lapham. Otherwise, I'll hopefully see you guys around campus in the fall, and if you need any help studying for finals, same things apply to that as well. So good luck, and I will hopefully see you guys sometime soon.